Hey Phys 1 kids, Campbell here. In our fourth video on one-dimensional kinematics, we're going to talk about the equations of motion. So we're going to finally do some math. Now, when we're moving with constant velocity, remember that our object has zero acceleration and we have equally spaced intervals on a motion diagram. And our position versus time graph, right, is a nice slanted diagonal line because we have equal displacements over equal time intervals. And then we can use this equation that says velocity is the change in position over change in time. In fact, we could rearrange this for position and get the final position is equal to the initial position plus the velocity times time. In fact, remember we talked about the area under a velocity versus time graph is that displacement. Well, you can actually see that here, right? Base times height is right here, and that will give me my final position. And of course, I need some initial position added to that to get my final position. But when we have constant velocity, then the displacement is directly proportional to the velocity and the time. So if you double one, then the position doubles. So if you double velocity, position doubles. If you double time, position doubles. However, when we have constant acceleration, right now our graph, our position versus time graph, is a curvy graph. And so that velocity is the change in position over change in time only gives us an average. It doesn't tell us what's going on at any instant in time. And our velocity graph, remember, then it becomes a slanted line. And we have an acceleration equation that we can use when we have constant acceleration that says that acceleration is the change in velocity over change in time. It kind of looks like that velocity equation. And of course, we could rearrange that equation for final velocity, which gives final velocity equal to the initial velocity plus acceleration times time. In fact, remember that the area under an acceleration time graph, area equals base times height, acceleration times time, will give me my change in velocity, or the final velocity if I have an initial. But now when I look at the velocity graph and I want to go from velocity, the area under a velocity graph, to a position graph, it becomes more complicated because now I have a triangle, right? And so then I have to use like a half of the base times height. And if I start at some initial velocity that's not zero, then I've got some more space to add in. And so I have a new equation that I need to use for displacement when there's acceleration. And it's this equation: the final position is equal to the initial position plus the initial velocity times time, right? That's that first part of the equation for when we had constant velocity. But now we need to add this additional term, the 1/2 acceleration times that change in time squared. So anytime I have acceleration, now my position has a quadratic relationship with time. So if we double time, then the position is going to quadruple. So there are three equations of motion that we're going to use when there's constant acceleration. The first one is, I call this my favorite equation. We saw that on the previous slide, and what I did is I copied the actual equations from your equation sheet that you get on the AP exam, and you can, so these X's might kind of freak you out, these little X's here, but just kind of ignore them. So when velocity changes steadily, my velocity at any position is equal to that initial velocity plus the acceleration during that time times the time. And here's that displacement equation I showed you from the last slide. So my position at any time is equal to the initial position plus that initial velocity times time plus 1/2 times the acceleration times time squared. But we can also, so these two equations here, notice they both have time in them. But sometimes we don't have time, literally and figuratively. Sometimes we have information about position and velocity and acceleration, but not time. So if we combine these two, like we solve them for time and we combine them together, we get this equation. This says that the final velocity is squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position. So final minus initial position. So those are my three equations of motion. And anytime we are solving problems mathematically in kinematics, we will be using these equations. So how do we solve problems when we have constant acceleration? Well, I always recommend that you draw a picture of the motion. This is especially important if there's two phases of motion, like if I'm speeding up and then maybe I'm constant speed and then I slow down. So if I have different accelerations, we have to look at each of those segments separately. So it's always good to draw a picture. I always make a list of the 6 variables, right? There's initial position, there's final position, there's an initial velocity, there's a final velocity, there's the acceleration, and there's the time. So there's 6 variables. And so if you write them down and you label them out with your knowns and your unknowns, it makes it easier to figure out which of the 3 kinematic equations should you use. Now you only want to pick an equation that has that missing thing, that thing you're trying to find. You don't want 2 variables that you don't know in an equation, or you can't solve it without another equation. Once you have picked your equation, rearrange it and make sure you pay attention to the signs of motion. So if you're traveling to the left or down, remember that that velocity is a negative velocity. Very important, and of course time is always positive. So let's do an example. Here I have a Saturn rocket that's launched straight up with a constant acceleration of 18 meters per second squared. I want to know how fast the rocket is moving after 150 seconds and how far it's traveled. So the first thing I'm going to do is I'm going to make a little table. So I'm going to start with x final, x initial, v final, v initial, acceleration, and time. So 6 variables, doesn't matter what order you put them in. The final position, I don't know. That's one of the things that I want to find out. We're going to call, and if you see the little picture here, the initial position 0. The final velocity of this object, or the rocket, I don't know either, so we're going to put another little question mark there. Usually when a rocket blasts off, it starts at rest. So we're going to say, because we don't have any other information, that the initial velocity was 0. The acceleration, they tell us, is 18 meters per second squared. And we know that it is gone for 150 seconds. All right, so I have information about initial position and velocity, acceleration, and time. And I want to find out, first, how fast is this rocket moving? So I want to solve for my final velocity. Well, we're going to go with the easiest equation we have, and that's this one. V final is equal to the initial velocity plus the acceleration times time. So I can just fill this out, and I have 18 for my acceleration and 150. So I just have to multiply those 2 things together, easy peasy. And when I do that, I find I'm going pretty fast. That's 2,700 meters per second. Speedy. Woo! Well, I guess you got to be if you're taking off. How far has it traveled? Well, now we want an equation that has distance in it. Well, we have the distance equation that looks like this. X final is equal to x initial plus, let's use O's. Initial velocity times time plus 1/2 acceleration time squared. Let's see, I could use this equation because I know that this is 0, and I know the initial velocity, the initial velocity is 0, so that term goes away. And then this is just down to x final is equal to 1/2 at squared. So I can just plug in my numbers now. 1/2, the acceleration is 18, and the time is 150 squared. Don't forget to square it. That's something that's easy to forget. Those little squares, they're little pesky things. So if we do some math here, we're going to find out that you've traveled 202,500 meters. That's really far. Now, we could have actually even used the other equation, right? This equation, v final squared is equal to v initial squared, plus, that's supposed to be a plus, to a delta x, right? We could have used that equation as well because I have all of that information. So either one would have worked. We just would have had to do more rearranging with that second one. All right, let's do another one. Let's see if you can figure this one out. An airplane is flying initially at 120 meters per second. It lands on a carrier deck and stops in a distance of 91 meters. What is the acceleration of the airplane? Well, I drew you a picture. Well, okay, I didn't really draw you a picture, but whatever. Make your list of variables. Then figure out which equation you can use to solve for acceleration. All three of them have acceleration, so look at what information you have before you pick it. And then do some math and see if you can get it right. Pause the video and try this problem. So here's my data table. My final position is 91 meters because that's how far it takes to stop. So I called my initial position 0. Hopefully you recognized that when you stop, your final velocity is 0. Sometimes that can mess you up. And your initial velocity is that 120 meters per second. We're trying to find acceleration, so that's an unknown, but they also didn't tell us time. Oh, so that limits me, right? There are 3 equations and only one doesn't have time in it. That's that third one. It's this one. V final squared is equal to the initial velocity squared plus 2 times acceleration times that change in distance or displacement. Now, one of the things I want you to get in the habit of is rearranging the equation before you actually plug numbers in. So first, let's move over that initial velocity. So I get V final squared minus the initial velocity squared. That's equal to 2a delta x, final position minus initial position. Now we're solving for acceleration, so that means we need to get it by itself. So we want to move this over here. So that gets rid of that and that and that. And so now I have that acceleration is the final velocity squared minus the initial velocity squared over 2 times that change in position. That's a 2. Now we just got to plug numbers in. So our final velocity, remember we said we stopped, so that's 0, minus our initial velocity, which was that 120 squared, divided by 2 times 91 meters. All right, so if you plug that into your calculator, you're going to get negative 79 meters per second squared. Negative? What? Yeah, don't lose the negative, right? It's right here. Don't forget about it. Does it make sense that the acceleration is negative? I hope so, right? Because we're moving in the positive direction and we're slowing down, right? Because we got to stop. So that's negative acceleration. How'd you do? We'll do some more of this in class, so I'll see you in class.